All right. So with that out of the way, I'm going to bring up, I was going to say an old friend of mine, but I don't think he wants to be known that way. Jon Callas and I have been friends for many, many years. Jon, I'm probably going to let him introduce himself because I think he'll do a better job than I will. But Jon has been involved in the security industry probably longer than just about anybody at this point, having done many different things, including PGP and now Silent Circle. But I think you're going to be a better person to introduce yourself. So Jon, please come up and introduce yourself and amaze us. And which is better
Thank
for you?
Thank you very much.
You want this one or you want to go with that? It's up to you.
Actually, the one of the lavaliers is better.
Okay, why don't you take that? And okay. And that's your presentation.
That's my
Should be
presentation.
good. Okay. I'll take that here now. I'll take that.
All right, can
it's
you
all
hear
yours.
me? Okay, that's good, because I think I can hear me in the speakers. So Leonard asked me to come and talk about digital signatures or something like that. And so I took that to heart. It's going to be about digital signatures. As he said, I'm one of the co-founders of PGP Corporation. I'm one of the co-authors, editor that standardized OpenPGP and a number of other digital signature related standards like DKIM, which is one that is now being used for email content control. I don't want to say anything like anti-spam because that's part of it. Syslog sign, which was originally done by our friend Jon Callas, who's now at NIST, and we standardized that and updated it for the IETF. I was one of the people who did the stain hash function, which was one of the finalists for SHA-3, and along with that, the three-fish cipher. I worked at a number of places, including Apple, where one of the things that I did was the crypto design, and I was one of the implementers as well for File Vault 2, which I hope you're running on your system right now. I don't really want to make this be technical with math and crypto and stuff because digital signatures are really a semantic thing. They are all about taking some sort of data and making an authenticity seal around it. I would go so far as to say that when we created the word signature, it was probably the wrong word. Digital signatures behave far more like a seal than they do like a signature. If you really want to get picky, a signature is an act. When somebody hands you a credit card slip to sign, they actually don't really care what you write on it. What they care is that you did it, and it is the act of signing it, not the actual where the ink bits went. Whereas digital signatures are an authenticity mark. They let you know that a stream of data or a blob of data is intact and that it is unmodified. So it hasn't had anything added to it, subtracted from it, or changed anywhere in it. There's two broad things that are like signatures. One that we call digital signatures, and that's what most of this will be about. But there's also something called MACs, or message authentication codes. And these are done with symmetric keys like AES or hash functions themselves. And don't worry, there's not going to be much more actual crypto here. The idea behind a MAC is that there is a shared key that the people who can read it can use to authenticate the data. The advantage and the disadvantage of this is that if you can check that the data was whole, you could go and rewrite it yourself. It is a completely shared read-write experience. And that has a lot of advantages and a lot of disadvantages. MACs will typically be used on communications protocols. They're starting to be used in ciphers because there's now cipher types that will do both encrypting and MACing at the same time. But the advantage of these things is that it is a fully live experience for how you deal with the data. That's also the disadvantage of it, because it means that you can't use this for anything like archival, because anybody who could verify the MAC could also change the data. And that brings us to the digital signatures themselves. You know, I know that PDF does signed documents themselves, and I've been doing a lot of that with myself. They use public keys, and the advantage of this is that there is a key that is the signing key that the signer keeps private, and then there is a key that is the verification key, which is a completely public thing. It can be stored on a website. Anybody can have it. So you have two separate actors in here. You have the world at large that can verify this signature, and you have the signer itself. The real advantage of this is twofold. One, you have the object and you can verify that the object is what you really hoped it would be. And the other is that you know that the signer did this. So it becomes a lot like a voice, that so-and-so says that this thing is good. So, you know, for example, Adobe says that the application on that floppy has not been modified and is whole. Each one of these things, the fact that you can check the object and the fact that you can check the signer, are in fact separately interesting and valuable things. My last little technical bit, which is that the algorithms that typically get used for this, one is RSA, which is also the public key algorithm that is used for a lot of other cryptography, and the other is DSA, which is the digital signing algorithm. And you will also hear that as DSS for the digital signature standard. The difference is merely like tweaking the parameters. The standard has a set of defined parameters. The algorithm will take a generic set of them. Elliptic curves are a new type of public key algorithm. They are exactly like doing DSA over large integers, except that it is using a bent curve. And I could go into this in detail, but it would probably bore you. So I'm not going to. I'm going to say that when somebody talks about the difference between eDSA and something else, it really is DSA, and it just happens to be using this other set that's not the integer. The reason why we do that is that we get better crypto strength with shorter keys. If you want to have a digital signature that is of what we would consider to be a decent size now, you'd be using 3000s or bits or better for RSA or integer DSA. Whereas when we talk about crypto strength with ECC, it is exactly twice the number of bits. So if you want 128 bits of security, you use a 256-bit key. There's the last bit of real crypto that I'm going to bore you with. Now, in one of these traditional signatures that I talked about, the object itself that you are signing is not directly signed itself. And this is for performance reasons. The signing algorithms are several orders of magnitude slower than what you would do with a faster algorithm. So what we do is we take a hash of that object, and that is merely a fixed length representation of it that statistically is not going to be duplicated by anything else. Hash algorithms are a black art in themselves. I've been involved in that. And the quality of the hash function is really important to a digital signature, because if the hash algorithm is broken, you can forge, duplicate, etc. digital signatures. Older algorithms that we used, like you will have heard of MD5. MD5 is easily broken. There's all sorts of mischief that people have done with creating duplicates and collisions. Collisions being two things that produce the same hash number. With MD5, there is another algorithm called SHA-1 that is in the process of being broken. We've known there have been flaws with it for a decade. They are finally coming to a head of it being operationally broken. There was, just like 2 weeks ago, a new paper on a better break on them. And while it is not practical to do so yet, it's definitely on its way to being broken. So you take the hash algorithm, one of the newer ones, you hash the object, which doesn't necessarily have to be contiguous. There are a number of interesting things like code signing algorithms where they will sign code that happens to be in pieces. With PDF, for example, you may want to sign pieces of a bundled document that has attachments and so on, and not others. There's no reason why you have to sign the whole thing. You could sign pieces, you could have separate signatures over each. So, if you think of something like text with an embedded picture, you could separately sign the text and the picture and have different characteristics based upon that. The signing key is, as I said, effectively making a statement. It is that the signer says that this thing is good, that it is whole and intact. However, one of the advantages and disadvantages is that any key can make a signature. There's nothing that keeps algorithmically only special keys doing this, and that means that you may want to know exactly who is making the signature, which I'll get to in a moment. There's also an interesting issue of signature stealing, and this is, I take a public key because a public key is a public object, and I wrap my name around it, and I say this public key is mine, and so therefore I'm effectively claiming that anything that it's signed is mine. I can't mathematically prove that because I don't have the private key that's the signing key. Somebody who wanted to challenge that would say, oh, really, that's yours, then why don't you, produce another one for us? And that wouldn't happen. There are protocols and systems in how we do things. In PGP, one of the ways that we did this was that when you declared a name, you signed the name yourself. And that way you proved that you had the private key for any name that you claimed. In the traditional certificate world, it's hidden behind the scenes that when you request a certificate from a certificate signer, the request that you send is a self-signed request. And that, as I mentioned, gets us to, okay, so who is the signer? In a lot of cases, the signers just identify themselves. I mean, for example, go to a code repository where someone has code that was signed with a PGP key. They will do something like say, here is the key that we use to sign our code releases with. And you can use that to verify any of the code releases. Of course, none of us actually do, but you could if you wanted to. The authenticity of that is based upon whatever you consider the authenticity of the web page itself. If the web page was delivered to you over SSL, you have a certain assurance on that. But often we simply say, okay, these people are the developers, they signed the thing, and we will do it that way. Sometimes you want to have a certification of that, and that would be some authority saying, here's who that signer is. And certification itself brings up an entire new can of worms. The biggest part of why this is a can of worms is that a certificate is a data object that binds a key to some information like, a name, an email address, or something like that. And it signs the two of them that says that this user data or this human readable, human usable data is bound to this key, so you can consider the actions of this key to be the actions of that name or whatever. And now we are verifying signatures with signatures. And thus the question is, so how do you verify that one? There's the question of then who made the cert. The traditional way that we do this is through authorities, and they're called certificate authorities, and they are people who have their own keys that they keep safe in hardware modules or using some certificate process. There are both legal and standardized ways that a certificate authority becomes one. I've gone through the process of doing this, and it's kind of like becoming a notary or something like that. But you end up with the question of who are these people? It's like, who made you God? Why did you do this? And often the answer is, well, I filled out a whole bunch of forms and did an audit and other things. And I'm going to go now into something that is a slight rant. It's a rant that pre-Snowden I would have elided away, but ever since these Snowden releases have come out, I've discovered that rather than being somebody who's on the far end of crypto politics, I'm now really kind of middle of the road. And here's something of a rant that I will go through on this. In the early days of cryptography, when cryptography was a tool of nations and military, because they used it to great effect during the Cold War and World War II, they used digital signatures and MACs as a way to control the use of crypto. There are a lot of diplomatic and military cipher systems where the keys that are used in them are not only key material, but they have been mapped themselves so that you know that the key came from the right place, so that the machine or process won't operate on arbitrary keys. When the very early standards came out, they used certificates to control who could use crypto. They wanted it to be used by only the good guys. In the early 90s, I was a developer at Digital Equipment Corporation on the VMS operating system, and we had a lot of secret things that we didn't want to talk about openly, and that included, important bugs and things like that. There was a brand new standard called PEM, for Privacy Enhanced Email, and that heavily influenced PGP, and it ultimately evolved into S-MIME. And in order for me to get a PEM certificate, I had to mail off my passport to MITRE, a government contractor, where they kept it for 2 weeks and then finally gave me back an email, a certificate that I could use for secure email, which I found really frustrating at the time, because I have never liked handing off my passport to anyone, and I also felt like, I have all of this data that shouldn't be around in the clear. Why are you making it hard for me to secure things that need to be secured? Since then, I do in fact point out that it was harder for me to get a certificate in the early 90s than it was to get a Saudi Arabian visa. So these were tools that they used precisely because they wanted to control who used it. And built into a whole bunch of our systems that revolve around certificates that are there to this day in SSL and so on, there's the idea of you want to make sure that someone who has a certificate is somehow a good person. This is not necessarily a bad thing. I mean, there are, in SSL, the EV, which is Extended Validation Certificates. You will have seen these be used when you go to any site in your web browser that puts up a green bar or green decorations about it. These are entities that have actually had some vetting done to them. That if you want an EV certificate, you have to be looked up in Dun & Bradstreet. You have to have a bunch of other processes done. The names that are on the certificates have to be only names that you are entitled to use through recognized way, like it is a trademark that you definitely own, it is something that is on your incorporation papers, and so on and so forth. That this vetting that is done intentionally to make it so that the people who read a signature, which includes, for example, a website, that is signed by this certificate, can have some assurance that that is the actual real Amazon.com or whomever that you want to go to. This is really valuable. But in a lot of cases, like arbitrarily signing a PDF that you would send off to a whole bunch of people, why does this need to be done by anyone other than, say, I'm the author of this document, why can't I just sign this thing? The major issue in the CA architecture is that there's the club of how you become a CA, and they are all equal inside the club. There are proposals and limited ways that they can scope themselves, but any certificate that is issued by one of these people is as good as any of the ones that is issued by anyone else. And this is what causes a lot of the consternation about the web today, because CNNIC, which is the Chinese national certificate authority, is just as good as VeriSign or Symantec as it is now. And there are a number of these around the world that do various things. They have their own forum. I was CTO for a couple of years at Entrust, which is one of the major CAs. And in this forum, there's a whole bunch of things that they discuss, probably similar to the things that you discuss, which are very interesting, which include obscure questions that somebody's got to take care of. One of the ones that I will give as an example was that there were people in Kosovo who wanted to set up, as part of the Kosovo government, their own set of certificates, authorities, and so on, and they wanted to do this under the aegis of someone else. Well, there are a set of countries that recognize Kosovo as a country, including US, most of Europe, and a set that do not. So we had to have representatives decide what it is that we were going to do, because Kosovo doesn't have an ISO country code like US, UK, DE, etc. So we had to come up with something that we would use, and the people who didn't recognize it had to essentially agree to hold their nose while the rest of us did this. There have been other issues, like a few weeks ago, VeriSign/Symantec accidentally generated a Google.com certificate that was not an authorized Google.com certificate. There were incidents 5-6 years ago where the Iranian government did hack attacks on a couple of CAs, including a Dutch one that ended up going out of business because of the results of this, where they got Google.com certificates, which allowed them to intercept not only search traffic to Google, but hand people updates to software, Chrome, and so on and so forth that were their updates. The set of authorities is something that's baked into a platform, and what I mean by a platform is like an operating system. They're built into Windows, Mac OS X. They're built into major browsers like Chrome and Firefox. And how we deal with the fact that they are all equal is in fact one of the huge semantic problems that we're going to have to deal with as we go down the line. And so here's one of the things that I will say. Identification certs are ultimately a tautology. Somebody is saying that this key goes with that name, but who says that the person who says that is actually that person? Who gave them the authority to do that? It really is, at the end of the day, one big agreement that we all said that we're just going to pretend that this all works. And fortunately, for the most part, it does. A slightly related problem is conflating reputation with a signature. Code signing, also a lot of email signing, do this, or explicitly don't do this. I mean, I will give an example from DKIM, which is an email signing system, where the idea behind DKIM is intentionally a low-value thing. The idea is that the signature on the email, which is backed by a key put in DNS, says that that domain is responsible for having put that email into the email stream. Sometimes this is a really high value and you want to know with it, because this is how, for example, you can know that a bank actually sent it. And an advantage of this is that if I am an email processor, I can quickly verify that a Bank of America email came from Bank of America and not someone pretending to be Bank of America, and thus I can treat it with somewhat more of a red carpet than I would otherwise. But on the other hand, even when I know that something that comes from yahoo.com, we know that Yahoo is generous where it hands things out, so just about anybody could do a Yahoo thing. And you don't necessarily want to test the content of it, trust the content of it, but you do know that if you don't like this thing, it looks like it's a Nigerian spam, that Yahoo are the people who are responsible for having put it into the email stream. So you go to the sysadmins at Yahoo and say, hey, I found this phishing mail and it came from your site. There are code signing systems that also imply that the code is good. This is one of the things that happens in a number of things in Windows and has led to a bunch of problems, like it is assumed that a driver that comes from a hardware manufacturer is in fact perfectly reasonable and you ought to just let it run. This means that in some of the major interesting nation-state attacks, including Stuxnet, behind that, there have been stolen certificates where they go to some small manufacturer of a hardware device in Malaysia or whatever. They steal the certificate from that person, sign the malware with the same malware that would have been done with, say, an Ethernet driver. And then it gets distributed around and the end of the operating system loads the malware, just like it would have loaded the Ethernet driver. And the reason for this is that system conflates the signature with reputation. It assumes that if this company did it, it must be good. This is an implicit part of a lot of the code signing systems, and a better way that I'm going to get to is to somewhat separate those things, separate reputation from the fact that something was signed. As I mentioned before, EV certs are a perfectly reasonable way that you do reputation, because a non-cryptographic process, something that is an actual procedure in how the operation of getting one of these is done, where the people who get the certificates actually have been vetted. There actually is something that is behind what they do and how they operate. That this is a completely reasonable thing to do because the certificate does mean reputation. The broader question then becomes, what does a signature mean? I mean, when you have signed something, the very first thing that I said was the syntactic thing. It says that the data that you have has not been modified, it hasn't been added to, it hasn't been subtracted to. You have exactly what it was that the person who sent it to you wanted you to have. But, what does that mean beyond just here's a thing and it's intact? Even more so, what does signed dynamic content mean? This is a question that a lot of people will have. I mean, I will go, for example, to Google Maps, and Google Maps will tell me something like it's a 10-minute drive here. Well, in another 5 minutes, it's going to be slightly different. What exactly does the signed content mean? This is one of the things that people have wrestled with. There was originally in how certificates were done, because they came from this government, banking, etc. There was the idea of, well, there must be liability associated with it. In what has transpired, really, liability isn't really an issue. It's kind of silly. I think the better way to handle this is what I call agnostic certificates. They aren't really saying much of anything. The signature is both a tag and a key, and take them for what they are. So, let's take the case of signed apps. The signature that is on an app is a really handy little thing because it is a very short, fixed length identifier that you can use to know this application, and that being different from essentially all other applications. If we did something like virus scan it once with the world's best virus scanner that took an hour to run, you could flag it in your virus system via the signature as good or bad. You could do something like have code that was crappy code developed by a good developer. I mean, you know, it's like we've all shipped bugs. You could take something that was a version of software that was known to be a buggy version and you don't want to be load. You could have a code signing system have a blacklist that would know, don't load this version of the software. I mean, you know, in general, we trust this developer, but this version we know is a bad version, don't run it. Go to a second process that says, you know, you have an old version, please go here to update it. This would be a much better way to handle things. The systems that we're starting to see on mobile devices go towards this. If you look at the signatures and systems that are done through iOS, Android, etc., they are not considering a signature made by a developer to be an automatic, it will be run decision. It will then go to further decisions that go on there. Android is moving towards being able to dynamically recognize bad content even when you've done something like sideload it. iOS, Amazon, etc. will be able to do things like remove things from stores, make things that are known bad not be runnable through whitelists and blacklists. There are also enterprise systems that are building whitelists of apps to run. So they will produce for the people in their company a list of what are the known good apps that can be run, and they have an add-on system that allows only those apps to be run. And those apps are typically identified by the digital signature that is on the app themselves. The advantage of this is that you can have something where you can establish a reputation for the object itself on a case-by-case basis, and you can also use a lot of that to move up the chain. So, you know, if you know that this is a signing key that has only ever developed malware, you could stop anything done by the signing key, which would be a shortcut from the device itself. But you can have known things where, for example, a specific app from a good developer could be banned, or you could, in the case of, say, a genuine signing key theft, know that, well, while this signing key needs to be retired, there are specific things like, you know, drivers, etc., that are nonetheless still good because they were produced before that. And my bottom line on this is that signatures are what you make of them. There's a lot of things that you can do with them. And we've made a lot of decisions over the years that didn't turn out to be as good as they could have been. They were well-intentioned and had lofty goals, but as we've gone on through the last couple decades of effectively signing things, there's huge differences in how we can work differently. And that's really the message that I have for you guys, because signed PDFs are extraordinarily valuable precisely because there's the idea that they are a digital equivalent of paper. Authorities that do things are often not necessarily authoritative. You have to look at things with the proper jaundiced eye. You have to look at things with your own interpretation. And of course, you know, syntax and semantics are not necessarily the same thing, but all of this information, everything that is done with that has value. The signatures themselves, because of the math behind them, are in fact valuable things that you can do a lot of very powerful stuff with. And that's it for me.
Great. Thank you very much, John. Are there any questions?
Hi, you mentioned that because some issues, some certificates were issued to Google, to other parties for Google, because of that there were updates possible to Chrome. But is that not taken care of by certificate pairing, which Chrome does, and so we effectively
Yes.
issuing the certificate of third party would not really matter in this case.
That's precise. You know, those are the real world incidents of why we do certificate pinning now. That certificate pinning is it's a relatively fancy name for a simple thing. If I'm doing an SSL connection to some other host, the host will hand me the certificates that verify that, and because any one of the authorities could have verified it, what I do in my app is that I look at the certificates that were given to me where the host is telling me, I believe that this is, well, you know, you should trust this connection, and here's the documentation of why you should do it. And I code into my app what I expect there to be. So, you know, so I would put the exact certificate or one further up the certificate chain of what I expect, compare them, and I don't do anything if it goes there. Certificate pinning is really valuable because it gets rid of this. It does exactly address the problem of, so who's an authority and what are they allowed to say? The downside of it is that if I want to change my certificate because it has expired its useful life, or I want to change providers or something else, I have to update my software before I update any of the servers themselves, and sometimes this can be a bit harrowing. There was an incident that we had at my company, Silent Circle, a year or so ago, where we realized that a certificate was going to expire in 2 weeks, which meant that we had to get new versions of the app out. It was one of those things that somebody said, oh, hey, this thing is going to expire, what are we going to do about it? And that meant that we went through a fire drill of updating the apps. Nothing's perfect, and there are lots of ways to do that. Ask me if you want more details.
In Europe, in July, we'll have a new regulation for digital signatures for signing in Europe. And I know that they've done an awful lot of work around vetting the CAs and actually having a trusted list of qualified signatures around pre-qualified CAs. I just wonder what your sense of, have they done best practices? Is that going to be a model that stands? And what do you think we'll learn from that?
This is a really good thing that they're doing. It is going to help a whole bunch of a number of the issues that we have, but it is something that helps rather than solves. And one of the reasons that it helps rather than solves is that there are certificate authorities that are not in Europe. There are certificate authorities that will want to comply with these rules, but there's certificate authorities all around, national authorities that are done for various purposes in lots of countries themselves. You know, for example, you know, one of the issue that I had with the Kosovo thing was precisely one of these where there's going to be skew on what it is that people believe. There's also still the idea of what happens when someone makes a mistake. The one thing that happened 3 weeks ago with Symantec misissuing a certificate was that it was a genuine mistake, and there have been genuine mistakes before. It's both really easy to over-wring one's hands over this. You know, a number of my security friends tend to blow this up into a worse problem than it is, but it is nonetheless a real problem that those of us who are the consumers of these CAs have relatively little recourse when somebody who's a member of the CA club, no matter how well that does, makes a mistake. If you're a big entity like Google or Amazon or BT or Vodafone, this is a much bigger issue than if you're relatively small and you don't really care about it. So yes, it's a really good thing to happen. It's good because we have not had these things in the past. but it's not a technical solution, it's a policy solution. And ultimately, when the policy goofs, the code does what it thinks is the right thing.
One more question, if anybody has one. Huff has one. Okay.
Hi. So I was struck by something you said at the outset. Signatures really should have been called seals. Think there's any scope to rebrand?
I don't think so. I think it is something that is baked into what we do at too low a level. We've been calling things certificates for so long signatures for so long that that's what we want to call them. We could start calling them seals, and there are a bunch of places where that's starting to happen. In the new financial credit card transactions that are going on now, there's the consortium that runs that's called EMV, which is for Eurocard, MasterCard, Visa. They are coming up with a whole bunch of new standards for how to secure those mechanisms, and they're starting to use more subtle words like seal, because signature really does have a specific legal definition in a lot of cases that is different from what they want to do. And things could spread from a widespread new use of digital signatures where we start calling them and saying that they're seals or something like that. But it would be a multi-year process.
Great, John, thank you very much. So.